All right, so objective 4 is graphing polar equations by plotting points. We're not going to work in the whiteboard for this. This is just going to be all in the PowerPoint. So if you were to graph r equals 2 times the quantity 1 minus sine theta, the first thing you want to check for is symmetry. To be quite honest with you, I'm not really sure why we have to include all of that. So I guess I will tell you that you can practice checking for the symmetry, and I will give you bonus on your exam if it's not required. But basically, you should be able to just find the points and graph it. And then by doing that, you should be able to see where the symmetry is. I guess the reason why they have you practice it is so that when you graph it, you know if you're making a mistake or not. It's definitely worth practicing. I just don't feel like you would need to do it all the time. So to check for symmetry of the polar axis, we want to plug in negative theta and see if we get the same result out. We don't, so then the test fails, but the graph could still be symmetric or not. It just depends on, I guess, the graph itself. All right, then you want to check for some symmetry along the line of theta equals to pi over 2. So you're going to replace theta with pi minus theta. Here, the test is satisfied, so the graph is symmetric with respect to the line theta equals pi over 2. And then they also check for symmetry with the pole. So they replace r by negative r. The test fails, so it may or may not have symmetry with respect to the pole. All right, so this is the main part that you need to worry about. We have to identify the points on the graph. Again, it's totally up to you guys, but I would just use Desmos. You can obviously find your points without using Desmos, but when you go to actually graph, I would just use Desmos. I wouldn't graph anything else, or I wouldn't graph using your regular calculator. So now you're gonna plot the points, and you can see they used a calculator, or they actually plotted it by hand. If you use Desmos, you can do a snippet or a screenshot and include it in your exam. Do me a favor, don't not include the images. You can do it by hand too. I'll probably give you bonus points if you do it by hand. But don't not put it on there, because then you end up missing points. All right, so definitely write this definition down if you are one of the students that writes it while I go. So the example we just went over is a cardioid, and it's characterized by r equals a, and then either it's going to be 1 plus or minus cosine theta or 1 plus or minus sine theta, where a is always going to be greater than 0. The graph of a cardioid passes through the pole. Okay. So the next example we're going to look at is an example of a limacon. I'm sure I'm pronouncing that wrong. If any of you know how to pronounce the C with the little extension, let me know. Without inner loop. So this is why this section is so long. It's literally taking us through all the different little nuances of graphing in the polar system. Again, they check for symmetry first. So that's the process you want to go with. Check for symmetry of the polar axis, the line of theta equal to pi over 2, and the pole. Once you check for all three symmetries, then you find your points. Okay, so it's the same process every time. And again, you don't have to do the symmetry. I'm not going to require it of you unless it's obviously the question on the test. But if you give them to me, I will definitely give you bonus points. And again, I will also give you bonus points, which could significantly help if you don't like Pearson as much. Then if you also give me drawn out, hand-drawn graphs over the taking a picture off of your calculator or taking a picture off of Desmos. I would definitely verify your pictures with Desmos or your calculator if you're doing it by hand. Okay, so here's definition number 3. Limacons without an inner loop are characterized by the following equation forms. A plus or minus B cosine theta, or A plus or minus B sine theta, where A and B are both greater than 0 and A is greater than B. The graph of a limacon without an inner loop does not pass through the pole. And a side note, while you guys are writing that down, did everybody register for the spring? Registration is open. I cannot tell you as of yet what I'll be teaching, but you guys are in one of the higher math classes. So you potentially wouldn't have me again unless you need to take stats and probability, but I'm still waiting for my schedule. I definitely do wish you all luck with next semester. Math is the greatest. If you haven't signed up for another math class, you definitely should. All right, so this is an example of a limacon with an inner loop. Again, they're checking for symmetry. You want to check for polar axis symmetry, the line of theta equal to pi over 2, and then also with the pole. You find your points. And then this is pretty cool. So they're showing you kind of in pieces. So they're showing you the first half and then they bring it all together. And then here's with the graphical representation from the calculator. Again, I'm not going to require it unless it's required on the exam. All right, limacons with an inner loop are characterized as the following. Here's the difference. A is now less than B. If A is less than B, then you're going to have an inner loop. The graph of a limacon with an inner loop passes through the pole twice, hence the loop. You guys remember that polar equations are how we get the really pretty graphs in math. Okay. So the next example is a rose. Same thing, they check for their symmetry. First, they check for the polar axis, then theta equals to pi over 2, and then the pole. They create their points. Okay. And then here they're showing you again, here's the first part of it. And then you can kind of almost envision where the rest of it's going. But there's your rows. Here it is on the calculator. So definition number 5, which is obviously the part you want to write down. Rows curves are categorized as the following: A cosine n theta or A sine n theta. And the graphs that are rose shaped, if n is not equal to 0 is even, the rose has 2 n petals. If n is not equal to plus or minus 1 and is odd, the rose has n petals. Okay. I think those are really pretty. That's just me. I think they're cool. Okay. Anybody want to take a guess as to how we pronounce that?
Lemniscate or something?
There you go. We'll go with that. A lemon skate. There you go. I threw an O in there. Yeah, it looks like that's what it needs. Okay, so let's take a look at what this one looks like. So for some reason here, okay, so it only took them 4 examples, but they have now decided that the symmetry is not necessary. They say we leave you to verify that the graph is symmetric with the pole. So they basically were only showing you that to practice it. They found their points and then they went through and they graphed it. So this is cute. It's kind of like a figure 8, a little bit. Yeah, figure 8. They are characterized by the form r squared equals a squared sine 2 theta and r squared equals a squared cosine 2 theta, where a cannot be 0 and have graphs that are propeller shaped. Okay, so, but can a propeller also have 4 sides or 3? I don't know. I would go with the infinity symbol. I guess it depends on what they look like. All right, we can also have a spiral, which is obviously going to be in the form of e to the theta something. They found their points, and then that's really cool. The curve is called a logarithmic spiral since its equation may be written as theta equals 5 ln of r, and it spirals infinitely both toward the pole and away from it. Okay. Go ahead and write these down. You have your classifications. They give you description. They also give you rectangular and polar equations. And then they give you the typical graph. And I imagine they're also going to give you the polar graph. If you want to take a look at So they're giving you just circles there. All right, so this is the coolest one. That's the one with the polar equations. If you need those again, I would definitely just watch the video and you can just scroll forward until you see those. Or you can pull open the PowerPoint. Remember, I use the I use the section PowerPoints. All right, so sketching the graph of a polar equation quickly. You should recognize the polar equation. It's a cardioid. So the period of sine theta is 2 pi. So just form a table and compute the R and plot the points. Okay. So there you go. That's the quick way of sketching it. They chose to ignore the symmetry, which is what I suggested for you guys to do from the beginning. Kind of looks like an apple. All right, any questions on section 10.2? Okay. Can you see section 10.3 or do I have to reshare it?
It's there.
It's there. Okay. All right. So section 10.3 is the complex plane in de Moivre's theorem. Apparently, math has decided I should just have to do some really great pronunciations today. So you can take a quick look at your objectives. So the complex plane, much like you guys probably could have guessed, is dealing with complex numbers. Essentially, x is just x, and then y is your imaginary number component. Nope, not what I wanted to do. So the x-axis is referred to as the real axis because any point that lies on the real axis is in the form of z equals x plus 0i, which is just equal to x. So it's a real number. The y-axis is called the imaginary axis because any point that lies on it is in the form z equals 0 plus yi. So it's a pure imaginary number. So if we were to plot the point z equals the square root of 3 minus I in the complex plane, then we would go to negative I, which we all know would be negative 1i, and then over to the square root of 3, which is right before 2. And we just plot it. That's it. Here's your definition. Let z equal x plus yi be a complex number. The magnitude or modulus of z, denoted by the absolute value of z, is defined as the distance from the origin to the point x comma y. So essentially, we're still working with triangles. So the absolute value of z is equal to the square root of x squared plus y squared. So I wonder if that technically means that z can kind of be related to r as well. Probably not, though. All right, the magnitude of z is sometimes called the absolute value of z. All right. Objective 2 is converting a complex number between rectangular form and polar form. All right. Convert a complex number between rectangular form and polar form. When a complex number is written in standard form, z equals x plus yi, it is in rectangular or Cartesian form because x comma y are the rectangular coordinates of the corresponding point in the complex plane. Suppose that r comma theta are the polar coordinates of this point. Then x equals r cosine theta and y equals r sine theta. If r is greater than or equal to 0 and theta falls between 0 and 2 pi, then the complex number z equals x plus yi may be written in polar form as the following. So it would be r cosine theta plus r sine theta I, and then you would just bring the I into the equation. So this is saying if z equals r cosine theta I sine theta is the polar form of a complex number, the theta is called the, I believe that says angular argument of z. And then the magnitude would just be the absolute value of z is equal to r. I knew it was going to be something like that. Yeah. Excellent. Do you guys have any questions on the definition part? I'm pretty sure we're going to do some examples, but do you have any questions on why all that is the way it is? Okay. So example 2, we want to write an expression for z equals negative square root of 3 plus I in polar form. So the point is located in quadrant 2 because x equals negative square root of 3 and y equals 1. So if r is equal to the square root of x squared plus y squared, so you just plug it in. And when you simplify it, you get the square root of 4, which is 2. So then sine theta equals 1/2 and cosine theta equals negative square root of 3 over 2, as long as theta falls within the boundaries. Okay. So the angle theta that satisfies both equations is 5 pi over 6. With theta equal to 5 pi over 6 and r equal to 2, then we get the following polar form. All right. I would definitely pay attention to these examples because they will definitely help you on your Pearson homework. Example 3, plotting a point in the complex plane and converting from polar to rectangular form. We want to write the expression for z equals 4 times the quantity cosine 60 degrees plus I sine 60 degrees. Well, we know what those are already. We're just going to plug them in. So we end up getting 2 minus 2 square root of 3i. All right. That one should be super easy for you guys. All right. Any questions on the first 2 objectives? No? Okay. All right. Theorem 1, we're going to let z sub 1 equal the following, and then z sub 2. So then we'll have z1 times z2, And as long as Z2 is not equal to 0, then 6 is possible. Equation 6 is possible. I'll give you a few seconds to write it down. Okay. All right. So finding products and quotients of complex numbers in polar form. So the first thing you want to do is you want to go through and actually replace the complex form for the polar form. And then you're just going to complete the operation. Okay. All right, so you can see that there was the replacement done. All right, so you're basically only multiplying the coefficients. And same thing with the quotient, you're just dividing the coefficients, making sure you get the right degree. Any questions on that? I'm sure if you come up with questions, you can always email me. All right, here's theorem 2. De Moravi's theorem, and I'm probably going to pronounce that different every time. If z is equal to r cosine theta plus I sine theta is a complex number, then it stands to reason that z to the n equals r to the n times cosine n theta plus I sine n theta, where n is greater than or equal to 1 is a positive integer. Okay. Need a few more seconds. I'll give it to you. All right, so if we're going to use this theorem, we want to write 3 cosine 30 degrees plus I sine 30 degrees, and we're going to raise everything to the third power. And they want us to write it in standard form of a plus bi. So we're going to distribute the cube to the outside, and then notice when you take it inside, because of the theorem, it becomes a coefficient in front of the degree. Well, I guess a factor in front of the degree. So then you get 27 times the quantity cosine 90 degrees plus I sine 90 degrees, which just ends up giving you 27i. If you're doing it on Pearson, they probably want the final answer. If you were doing it for me on a test and you liked leaving it the second to the last step, I would accept it. Okay. So now we have to write 1 plus I raised to the 5th power in standard form. So we can do it using an algebraic solution. They went ahead and just plugged in what they knew. Okay. And then once you work everything out, you end up getting -4 minus 4I. So this is showing you that some graphing calculators can go ahead and give you the output. You can try it with your calculator. If your calculator has an issue with it, I'm sure you can also use an online calculator. Again, since I don't make you guys do anything with lockdown browser or anything like that, you can definitely use online calculators. What I will tell you is if you're using an online calculator, A, you should let me know that, and B, you should definitely try to still write down your steps, because if you mess it up, then I can't give you partial credit. You can definitely use it for your homework and your quizzes, but I would definitely write it down if you're expecting to get the most amount of points. All right, objective 5 is finding complex roots. So we're going to let W be a given complex number, and then we're going to let n greater than or equal to 2 denote a positive integer. Any complex number z that satisfies the equation z to the n equals W is a complex nth root of W. Other than the fact that these can be related back to polar equations, I'm not really sure why we're covering them in this section. I guess they just didn't know where else to put it. All right, theorem 3, finding complex roots. Let W equal R cosine theta sub 0 plus I sine theta sub 0 be a complex number, and let n be greater than or equal to 2 be an integer. If W is not equal to 0, there are n distinct complex nth roots of W given by the formula. So that formula should look pretty similar to what you've worked with in the past, even though it's kind of expanded. Okay. Should be our last example for this set. We want to find the complex cube roots of negative square root of 3 plus I. We want to leave our answers in polar form with the argument in degrees. So that's pretty important, because I know some of you turned your exam 8 in using decimals and degrees instead of using radians and radicals. So you definitely want to pay attention to the directions. I didn't mark any points off, but other professors definitely would. So the first thing we want to do is we want to translate it from being in polar form, or from complex form to being in polar form using degrees. So they just rewrote it and then translated it. Okay, the 3 complex cube roots are the following. And they get k equal to be 0, 1, and 2. Again, these examples are definitely going to help you with your Pearson homework and the quizzes. And probably also the exam. So we're going to find the complex cube roots by doing the following. They just plugged in 0, 1, and 2 for k and solved. Okay. Any questions on 10.3? Okay. Keep moving because chapter 10 and 11 have a lot of material. Okay. So now we get to talk about vectors. We're going to graph vectors, find a position vector, add and subtract vectors algebraically, find a scalar multiple in the magnitude of a vector. We'll find unit vectors, find a vector from its direction and magnitude, and model with vectors. I do not believe we will get through this whole thing today, but it is 57 slides, so that is why I would like to go ahead and start it. So vectors, has anyone heard of them before? If you've taken physics or trig in high school, you definitely should have heard about vectors. In simple terms, a vector is derived from Latin meaning to carry, and that makes a lot of sense because it has to have both magnitude and direction. So typically when we shorthand vector, it's the symbol where it's just basically like an arrowhead, but with only half the arrow. The length of the arrow represents the magnitude of the vector, and the arrowhead indicates the direction of the vector. So when I'm saying, like if you were talking about vector A, you would shorthand it like that, okay? But then obviously when you actually draw a vector, it'll be different. Okay. Geometric vectors. All right, if P and Q are two distinct points in the XY plane, there's exactly one line connecting both P and Q. You can look at figure A. The points on the part of the line that joins P to Q, including P and Q, form what is called the line segment, which you guys should definitely know that from past courses. Right? Ordering the points so that they proceed from P to Q results in a directed line segment from P to Q, or a geometric vector, which is denoted by the following. Not really sure what that symbol is, so I would just draw, like if you see it down here, how they drew it down here. That is what I believe they're trying to do up there. I don't know why they showed it that way. All right. In a directed line segment, P is called the initial point and Q the terminal point, as indicated in the figure. Also, this arrowhead should be on the other side of Q. Or it should just stop at Q. It shouldn't really be in front of Q. It should stop exactly at Q. All right. Oops. The vector V, whose magnitude is 0, is called the zero vector 0. The zero vector is assigned no direction. Two vectors V and W are equal, then they are written as the following. If you bold a letter, then it's taken as a vector. If they have the same magnitude and direction, they are equal. Okay. Any questions on geometric vectors? That should basically have been a review for some of you. All right. We can also add vectors geometrically. So if we sum v and w, then the position the vectors v and w so that the terminal point of v coincides with the initial point of w. So that's important to realize. The vector v plus w is then the unique vector whose initial point coincides with the initial point of v and whose terminal point coincides with the terminal point of w. You can see it drawn out. Okay. Vector addition is commutative. I hate that word. That is, if v and w are any two vectors, then v plus w is the same as w plus v. All right, they're just drawn a little bit differently. You can see that it would still end up being the same summation line. Okay, same vector would come out of it. Vector addition is also associative. That is, if u, v, and w are vectors, then you can see the following. That one kind of looks like a kite. Right? The zero vector has the property that v plus 0 equals 0 plus v, which is just a v for any vector, which I'm sure you guys would have picked up on. If v is a vector, then negative v is a vector that has the same magnitude as v, but the direction is opposite. All right, this is kind of where some of it can start to get a little bit hard to wrap your head around the first time. So if you have any questions and you want something clarified, please speak up. If v and w are two vectors, then the difference v minus w is defined as v minus w equals v plus negative w. The figure illustrates the relationship. Again, it's another kite. Any questions on adding? Because that's basically what it is. Right? When dealing with vectors, real numbers are referred to as scalars. Scalars are quantities that have only magnitude. If alpha is a scalar and v is a vector, the scalar multiple alpha v is defined as follows. If alpha is greater than 0, then the magnitude is alpha times the magnitude of v, and it's in the same direction. If alpha is less than 0, then the vector is whose magnitude is the absolute value of alpha times the magnitude, and then they will be in opposite directions. If alpha is equal to 0, or if the vector is equal to 0, then no matter what, we get 0. Okay, so that still holds true. All right, you want to write down your properties. So 0 vector, of course, is equal to 0. 1 times the vector is equal to the vector. Negative one times the vector is equal to negative vector. You can see that you still have the distribution properties. and that you can also rewrite so that it kind of looks a little bit neater. Yeah, I feel like some of those properties aren't necessary, but I guess they can't just assume that you're all solid on your algebra from the beginning. All right. Any questions on the definitions of vectors before we get into graphing? No? Okay. All right, so example 1, you can see the following vectors are drawn out. You have v minus w, 2v plus 3w, and 2v minus w plus u. So take a look at those vectors, how they're drawn, because then you're going to have to combine them to be able to find your solutions. Right, there they are. You do not need to have a full-fledged answer. You know, a vector is a vector. You're not always going to know what it represents. So that is your solution types. All right, here's theorem 1. The symbol kind of looks like an absolute value, but with 2 lines on either side. Represents the magnitude of a vector. Since the magnitude equals the length of a directed line, it follows that the magnitude has the following properties. If a vector is a vector and if alpha is a scalar, then the magnitude greater than or equal to 0, the magnitude equals 0 if and only if the vector equals 0. The magnitude of negative v is equal to the magnitude of just v. And the magnitude of alpha v is equal to the absolute value of alpha times the magnitude of v, right? Any questions on that theorem? I assume we're going to have some examples on it. Okay. Definition 1. A vector u for which the magnitude u is equal to 1 is called a unit vector. Okay. All right, objective 2, find a position vector. So there were no examples with the magnitudes, so I would definitely pay attention to that slide if you get stuck on your homework. All right, an algebraic vector v is represented as it's a comma b, but do you see how the parentheses are kind of curved? That's done on purpose. All right, so that helps you identify that you're not dealing with just a regular xy plane. Where a and b are real numbers, scalars, called the components of the vector v. A rectangular coordinate system is used to represent the algebraic vectors in the plane. If v is equal to ab is an algebraic vector whose initial point is the origin, then v is called a position vector. Okay, you can see where the arrowheads are as opposed to the parentheses. All right. Theorem 2. Suppose that v is a vector with initial point p sub 1 equal to x sub 1, y sub 1, not necessarily the origin, and terminal point p sub 2 equal to x sub 2, y sub 2. If v equals p sub 1, p sub 2, obviously in vector form, then v is equal to the position vector, and there's the following. So they're kind of using a little bit of a unique distance formula there. It's not exactly the distance formula, but you, for all intents and purposes, you can pretend, if that helps you remember it. And then you can see they gave you a diagram to go with it. Okay. Example 2, finding a position vector. Find the position vector of the vector. So if v equals p sub 1, p sub 2, if p sub 1 is, so let's just practice that out. If p sub 1 is -1, 2, and p sub 2 is 4, 6, then what would we do? How would we find the vector?
You take the second x and subtract it from the first one, which is 4 minus -1, which would be 5. And then you take 6 minus 2 and you get 4.
Okay, so 5, 4. All right, there it is. Okay, so that was finding a position vector given an alternative vector. Okay. Theorem 3. Two position vectors v and w are equal if and only if the terminal point of v is the same as the terminal point of w. So this leads to the following: equality of vectors. Two vectors v and w are equal if and only if the corresponding components are equal. That is, if vector v equals a sub 1 comma b sub 1 and vector w equals a sub 2 b sub 2, then vector v is equal to vector w if and only if a sub 1 equals a sub 2 and b sub 1 equals b sub 2. All right, pretty self-explanatory. Right? Theorem 4. Let I denote the unit vector whose direction is along the positive x-axis. Let j denote the unit vector whose direction is along the y-axis. Then I is equal to 1, 0, and j is equal to 0, 1, as shown in the figure. Any vector v, a, b, can be written using the unit vectors I and j as follows. Right? So vector v would equal a vector I plus b vector j. The quantities a and b are called the horizontal and vertical components of v respectively. Okay, so you can write other vectors in the form of unit vectors. All right. All right, we can start this one. I just don't know if we will finish it. Just give me a second. Oh yeah, we can finish that. All right, definition 3. If we let vector v equal a sub 1 I plus b sub 1 j, again, I and j are your unit vectors, and w equals a sub 2 I plus b sub 2 j, be two vectors, and let alpha be a scalar, then we get the following. Okay. So it's just basically going through and showing you how to do vector addition and subtraction along with the scalar multiplier, and then finding the magnitude. obviously the magnitude of W there would be equal to the square root of A sub 2 squared plus B sub 2 squared. And then you can see that all of these points have been illustrated. All right, and then we do have an example. If we're given a vector 4i plus 2j, that equals 4 comma 2, and w equals 2i minus 3j, which is 2 negative 3, we want to find A. Part A is asking for vector v plus vector w, and B is asking for vector v minus vector w. So essentially, you're just adding and subtracting the like terms. That's it. So you collect up your i's. 4 and 2, we're adding, so that's 6i. 2 minus plus or minus 3 will give you a negative j, or 6 comma negative 1. Same thing with the negatives, or with the subtraction. 4 minus 2 is 2i, so that'll give you a 2. 2 minus a negative 3 will give you a 5. So 2i plus 5j, or 2 comma 5. We have about 20 minutes left. I can maybe do it. Let's try to do it. All right. Finding scalar multiples and magnitudes of vectors. So quite literally, you're just going to distribute 2 vector v. Well, the vector they gave you for v is 4, 2. So it's just going to be twice that, 8, 4. All right. If we were to do b, which is 3v, so I'm going to do 3 comma 2 minus 2w, which is 2 negative 3. We're going to get what here? We would end up with 12i plus 6j minus 4i plus 6j. And then you got to combine them, right? So 12i minus 4i gives you 8i plus 12j, or 8 comma 12. Let's see if we're right on that. There it is, 8, 12. You guys knew that though anyway. All right, magnitude of v. Did you have a question?
Yeah, so you just plug in what's in the parentheses?
Yeah, basically. So we had 3v. V was given to us as 4, 2, and then negative 2w. W is given to us as 2, negative 3. You have to figure it out separately and then combine the like terms. That's it. All right, so the magnitude of v, we have to find out the square root of basically your I unit squared and your j unit squared. So for the magnitude of v, it would just be 2 square root of 5. But if we go back and do the magnitude of w, what would it be? Well, the I component is 2, so that'd be 2 squared plus the j component. So that's going to be 4 plus 9, so the square root of 12, which is equal to 2 square root of 3. Okay. All right. Finding a unit vector. Okay. Unit vector in the direction of v. For any non-zero vector v, the vector u is equal to v divided by the magnitude of v. Is a unit vector that has the same direction as v. Okay. And then if you also rearrange it, you get equation 7. All right, so let's look at that with an example. If we're given the vector equals 6i minus 8j, or 6 comma negative 8, then we have to first find the magnitude, which ends up being 10. So then now we multiply v by the scalar 1 over 10. So we plug everything in and we end up getting 3/5 I minus 4/5 j. All right. You guys have any questions on that? So you have to find the magnitude first, and then you divide the vector by the magnitude. Well, 1 over the magnitude, so that's why they're dividing.
Yeah, so the magnitude of v is like the distance formula between the two coordinates.
Basically, yes. Okay. All right. Finding a vector from its direction and magnitude. Here's our property. If a vector represents the speed and direction of an object, it is called a velocity vector. If a vector represents the direction and amount of a force acting on an object, it is called a force vector. So this is why these are important. We're not just dealing with it in trig, you're going to end up dealing with it in physics as well. Okay. A ball is thrown with an initial speed of 30 miles per hour in a direction that makes an angle of 45 degrees with the positive x-axis. Express the velocity vector v in terms of I and j. What is the initial speed of the horizontal direction and what is the initial speed of the vertical direction? Okay. So the first thing we had to do is we have to find the magnitude. Well, the magnitude was given as 30 miles per hour. The angle between the direction v and I is 45. So then they just plugged it into the formula. And then they simplified. All right. The initial speed of the ball in the horizontal direction is the horizontal component of v. So that'll be 15 square root of 2, or 21.21 miles per hour. Then you have to find the vertical component, which is the same thing. So there it all is drawn out. I would definitely pay attention to this problem if you end up coming across one in your homework or on the quiz or exam, I guess, for that matter. Though you all know that there are examples within your homework, so you should be fine. All right, so if we are finding the direction angle theta of the vector equal to vi minus vj, the direction angle alpha can be found by solving tangent alpha. Well, we all should have guessed that one. So it equals to -1. What direction angle would that be? 315 degrees. So there they've drawn it for you. Sorry if I'm going a little bit quickly. I just want to make sure that we get this in so that we can start with the next section on Monday. Resultant force Because forces can be represented by vectors 2 forces combined the way that the vectors add. If force 1 and force 2 are two forces simultaneously acting on an object, the vector sum is the resultant force. The resultant force produces the same effect on the object that is obtained when the two forces F1 and F2 act on the object. So you can see the little diagram that they gave you, which basically is the same diagram from above, just with different letters. Excuse me. Okay, so we're going to find the actual speed and direction of an aircraft. We're told that a Boeing 737 aircraft maintains a constant speed of 500 miles per hour headed due south. The jet stream is 80 miles per hour in the northeasterly direction. We want to express the velocity of the 737 relative to the air and the velocity of the jet stream in terms of I and J. We want to find the velocity of the 737 relative to the ground and find the actual speed and direction of the 737 relative to the ground. Okay. So we're going to set up the coordinate system. You can see it at the right. All right, we were given that V sub A is equal to negative 500J. The velocity of the jet stream has a magnitude of 80 and a direction of northeast. So the angle between VW and I is 45 degrees. Express VW in terms of I and J. Well, you're going to plug in your 80 and your 45. And when you work everything out, you end up getting 40 square root of 2 I plus J. Now they brought the 40 square root of 2 out. You could have left it in. You could have done this 40 square root of 2I plus 40 square root of 2J, but they pulled it out to make it look nicer. The velocity of the 737 relative to the ground is equal to negative 500J plus what we just found for the velocity W, or vector W. So then we end up getting 40 square root of 2I plus 40 square root of 2 minus 500J. And you guys would have got that. So then we're just left with finding the magnitude. We get roughly 447 miles per hour. And then we use the tangent of alpha to find your angle. And it's important to note that it would be south of east. Okay. And that comes from chapter 9. I believe we did that in chapter 9. Okay. All right, finding the weight of a piano. Two movers require a magnitude of force of 350 pounds to push the piano up a ramp inclined at angle 20 degrees from the horizontal. How much does the piano weigh? So there's their nice little diagram, which, by the way, I can't remember who did it, but someone drew a bunch of diagrams, and you can ask them if you want. Definitely gave bonus points for diagrams on the last exam. So we're going to let force 1 represent the force of gravity and force 2 represent the force required to move the piano up the ramp. So then force 3 is going to represent the force of the piano against the ramp. So the angle between the ground and the ramp is the same as the angle between F1 and F3 because of the triangles A, B, and C and B, D, and E are similar. So we get angle BAC is equal to angle DBE, which is 20 degrees. And then we're just going to plug it into the magnitude formula. So you get an approximate weight of 1,023 pounds. All right. Static equilibrium. An object is said to be in static equilibrium if the object is at rest and the sum of all forces acting on the object is 0. So that would mean the resultant force is also 0. Apparently, this chapter likes to figure out how much pianos weigh. A box of supplies that weighs 1,500 pounds. Yeah, that's the wrong title. A box of supplies that weigh 1,500 pounds is suspended by 2 cables attached to the ceiling as shown in the figure. What are the tensions in the 2 cables? So here they went ahead and drew it for you on a XY coordinate. And then they just went through and plugged it in. Right? I would definitely go through that on your own in a little bit more detail. Just kind of showing it briefly so that if you watch the video later, you can take any notes down that you want. Also, the PowerPoints are all up on Canvas. So if you ever want to just go through just the PowerPoint, you can do that as well. So we end up getting the left cable has a tension of approximately 776.5 pounds, and the right cable has a tension of approximately 1,098.1 pounds. And again, if you watch the video or if you want to check out the PowerPoint, you can do that. It's up on Canvas.